Deep space images captured by telescopes like Hubble or James Webb reveal a universe shaped by spectacular structures. Giant pillars, isolated dark clouds, and cosmic formations drift through the void like glowing comets. But these structures are temporary, they are cosmic battlegrounds. At the heart of these views lies a powerful astrophysical process known as photoevaporation. Newly born massive stars flood their surroundings with intense, high-energy ultraviolet radiation and X-rays. Depending on the scale, the environment, and the stage of stellar life, this single process manifests in vastly different phenomena. It acts as both a sculptor of massive star-forming regions and a destructive force that can strip away the raw materials needed to build planets. This breakdown covers the distinct types of photoevaporation flows and examines the iconic cosmic structures left in their wake, including champagne flows, elephant trunks, isolated Bok globules, endangered proplyds, and enigmatic cometary knots. The process of photoevaporation operates across vast structural scales, beginning within the massive molecular clouds that serve as stellar nurseries. When a massive, hot star, usually an O or B-type star, ignites deep within a dense molecular cloud, it floods its immediate surroundings with extreme ultraviolet radiation. This radiation ionizes the surrounding hydrogen gas, heating it from a freezing 10 Kelvin to a blistering 10,000 Kelvin. This region of hot, ionized gas is known as an H2 region. Because this gas is extremely hot, its pressure increases and causes the bubble to expand into the dense molecular cloud. This is where we witness a phenomenon known as a champagne flow. As the ionized bubble breaches the boundary between the dense molecular cloud and the lower density interstellar medium, the high-pressure ionized gas bursts out of confinement, streaming into the empty space. This specific type of photoevaporation flow acts as a massive ventilation system for the star-forming region. It empties the mother cloud of its gas from the inside out, halting further star formation in that immediate area and launching a vast, streaming wind of ions into the galaxy. As the intense ultraviolet radiation from massive stars continues to erode the surrounding molecular cloud, it does not clear the gas evenly. Molecular clouds are inherently turbulent and clumpy, filled with pockets of varying density. The result is the formation of long, column-like structures pointing directly toward the source of radiation. These cosmic sculptures are known as elephant trunks or cometary pillars. The physics driving this structure is a combination of photoevaporation and compression. The ionization front on the side facing the hot stars heats the surface of the dense knot, triggering a continuous, outward photoevaporative wind. At the same time, this process drives a shock wave inward, compressing the gas within the pillar. This compression often triggers the birth of a new generation of stars directly inside the head of the elephant trunk. Newborn stars are often found right at the tips of these pillars. When they ignite, they release their own stellar winds and radiation. This internal force pushes against the pillar, creating small cavities and clearing away the nearby gas. This puts the tips of these elephant trunks in a double squeeze. They're being eaten away from the outside by massive neighbor stars, while simultaneously being hollowed out from the inside by their own newborn stars. As photoevaporation progresses, it completely detaches structures from their parent clouds, leaving behind isolated islands of gas and dust. These isolated remnants appear in two different stages of stellar evolution: the birth of stars and their death. On the birth side of this cycle are Bok globules. These are small, dark, and highly dense molecular clouds. While some exist independently in interstellar space, many form when the intense photoevaporation flow cuts through the base of an elephant trunk, severing the tip from the main cloud. Left isolated in a harsh environment, the outer layers of a Bok globule continue to evaporate. Yet, because the core remains extremely cold and dense, gravitational collapse can still occur inside, quietly forming isolated low-mass stars. A visually similar but physically distinct phenomenon occurs at the opposite end of stellar life, known as cometary knots. These structures are found inside planetary nebulae, formed when a dying intermediate mass star expels its outer envelopes and exposes its hot core, a white dwarf. The intense ultraviolet radiation from this dying core streams outward, hitting dense cold knots of gas that were previously shielded within the stellar wind. As the radiation ionizes the side of the knot facing the star, a photoevaporation flow is triggered. The heated gas expands and streams away from the central star, creating a glowing, ionized head. The unionized, colder molecular gas is pushed backward, forming a long, shaded tail. Although these cometary knots resemble actual comets, they are entirely gaseous structures, spanning billions of kilometers, shaped by the final photoevaporative gasp of a dying star. The final and most localized manifestation of this process occurs on the scale of individual planetary systems, outside the structures known as proplyds, short for ionized protoplanetary disk. When a low-mass star is born within a dense stellar cluster, it is surrounded by a rotating disk of dense gas and dust. This disk contains the raw material required to form planets. However, if this young system resides near a massive O or B-type star, it enters a hostile environment governed by external photoevaporation. The intense far ultraviolet and extreme ultraviolet radiation from the neighboring massive star bombards the outer edges of the young disk. This radiation heats the outer layers of the disk to hundreds or thousands of Kelvin, forcing the gas to overcome the weak gravity of the central low-mass star. As a result, a massive photoevaporation flow is triggered, launching a stardust wind away from the disk. The radiation pressure and stellar wind from the massive star sweep this escaping material backward, shaping the entire envelope into a distinct, teardrop-shaped cocoon that points directly away from the radiation source. Inside a proplyd, a literal race against time takes place. The external photoevaporation flow can strip away a disk's gas within a few million years, a blink of an eye in cosmic time. If gas giant planets like Jupiter or Saturn do not form rapidly before this flow depletes the disk, the system will be permanently starved of gas, leaving behind only the rocky materials to form smaller terrestrial worlds. Ultimately, photoevaporation ensures that nothing in the deep universe remains static. The structures we observe today are not permanent landmarks, but a fleeting snapshot of a past already gone. By the time the light from these distant nebulas reaches our telescopes, the intense radiation from massive stars has likely already rewritten the landscape.